Thermodynamics. Problem: Thermodynamical cycle. A closed cycle was processed with 1 mole of an ideal monatomic gas, shown in the figure, where 1, 2 is isotherms, 2, 3 is isobars, 3, 4 polytropic, the heat capacity of which is C equal R over 2, and 1, 4 isohoric. The minimum temperature reached by the gas in the cycle was 300 Kelvin. A polytropic process is a process that occurs with a constant heat capacity C. First question. Specify the points on the cycle at which the gas reached the maximum and minimum temperatures and determine T maximum. Second question. Determine the amount of heat supplied to the gas per cycle. Question number 3. Determine the work A of the gas per cycle. And number 4. Determine the cycle efficiency and compare it with the efficiency of an ideal heat engine operating between a heater and a cooler with the temperatures T maximum and T minimum respectively. Solution. Let's examine this cycle. So first we can see that if this process from point 1 to 2 isothermic, it means that the temperature during this process is constant. During process 2 to 3, that's isobaric. It means that temperature is increasing when volume is increasing. And here we have temperature greater than in point 2. Same thing here. Here we have isohoric process. It means that here temperature proportional to volume. And in point 4, temperature greater than in point 1. And during process from 3 to 4, that's a polytropic process. During this process, temperature either increasing constantly or decreasing constantly. And it means that temperature during this process cannot be less than minimum temperature during process 1 to 2. So this is how to find what is a minimum temperature during whole cycle. That's 300 kelvins. Second thing, during this investigation, a good idea to draw this table where we can show all macro parameters for process like pressure, volume and temperature. From this diagram we can see all these volumes, pressures and temperatures for all points like 1, 2 and 3. And we don't have only a number for point 4 where we don't have pressure and temperature, which we can count during this polytropic process. So that will be our next step, to find what is pressure and temperature during this polytropic process from point 3 to point 4. First we can write a universal gas law which works for any process. For monatomic gas it's like this: PV equal RT. And let's examine our polytropic process. For polytropic process we have this formula. The amount of heat applied to our gas equal to work done by gas, which is PdV plus change of internal energy for gas. which is 3 over 2 R dt. And as a result, it must be equal to heat capacitance during this process, which we already know, that's 1/2 R multiplied by dt. From this expression, we can immediately simplify it to move this part to the right, and that will be easy way. This is how to find what is R dt during polytropic process. Now let's rewrite this universal gas law in differential form. This is differential form. And now let's put this R dt to the right. This is how to express what is the dependency of volume and pressure during this particular polytropic process. Now we have to split our variables. It has this form. And now we can integrate this process from point 3 to point 4. We have this expression. We have a PV square, it's a constant. And now from this universal gas law we can express PV as RT and insert it here. We have this expression that T multiplied by V, that's a constant during this process. And because we already know what is volume in point 3 and 4, we can find what is the relation between T in point 3 and point 4. Now, from this formula, we can find what is T in point 4. That will be T3 multiplied by V3 over V4, which is 3T0 multiplied by 3 over 4, which is 9 over 4 T0. And the same relation we have for pressure, because for this process pressure proportional to temperature, and we have P4 equal 9 over 4 P0. Now we're ready to answer for questions 2, 3 and 4. So question 2. How many heat was added during this process? So we have to count what is Q in. Let's examine all 4 processes. So process from 1 to 2, that's isothermic process, and during this process internal energy for gas is not changing, but gas are doing negative work. So it means that here we have Q out. During process 2 to 3 we have isobaric heating, so it means that the gas doing work, and also temperature is increasing. So it means that during this process we have Q in. During process 3 to 4, this polytropic process, we have positive heat capacitance, but temperature is decreasing. It means that heat is out. And during process 4 to 1, we have isohoric process with pressure is down. It means that work by gas is 0, but the internal energy is decreasing. So it means that here we again have Q out. The only process responsible for heating, it's this isobaric process from 2 to 3. And for this process we can count immediately what is a total Q in. So this is the formula. Here we have heat capacitance for constant pressure, Cp for monatomic gas, it's 5 over 2R. We have to multiply it by temperature difference, T3 minus T2, and using this table we can count that this Q in equal 5R T0. And when we put here 300 kelvins, we can find numerically what is Q in. Next question is we have to find what is total work done by gas during this cycle. And the work done by gas, that's equal to total heat translated through all these four processes. It means that positive heat and negative heat. So first let's count what is heat out during polytropic process 3-4. We have heat capacitance 1/2 R, and we have temperature difference T4 minus T3. So this is our formula. Finally, we use this table. We use temperature T4 equal 9/4 T0, and we have minus 3/8 R T0 during this process. So this is Q out. Let's count what is Q out during process 4-1. During this isohoric process, heat capacitance equal 3/2R, and we multiply it by temperature difference, and we can count what is total Q during this process. That's this one, 3/2R multiplied by T1 minus T4, which is from table will give us negative 15/8 R T0. And the last Q we can count for isothermal process. So here we have a formula for isothermal process from our universal gas law, this one. Here we have temperature equal T0, and we can count this work done by gas, because when temperature is constant, internal energy is not changing. So we have to count only work done by gas. That will be integral from V1 to V2 P on dV, and P we can express from this formula. It will be RT0 over V, which is give us this result for integral RT0 logarithm V2 over V1, which is negative ln4 multiplied by RT0. Finally, we can count what is total Q out. That's this one. And to find what is total work done by gas during a closed cycle, we have to count all heat translated through this process. It will be Q in plus Q out. That's this one. This is the answer for question 3. And the last question is question 4. We have to find what is our efficiency for this process and compare it to Carnot cycle, most efficient process for T minimum and T maximum. So for this process we have this formula: efficiency equal work over Q in, which is about 0.27 or 27%. And for Carnot cycle we have efficiency, this one, that's 1 minus T minimum over T maximum, which is about 67%. So that's a comparison. That's it. This problem is done.